doing is that you're generating a completely new animal which was probably not there before, and it has to look like it's a dog, but it has to resemble or be a very different image from the images which you have given in the training sample. And we are now living in an era where this problem has been successfully solved. And generative AI works in many different modalities. I have shown 4 modalities here, that is text to text, text to image, text to 3D models, and text to videos. So the applications of generative AI are a lot. Every month there are new and new applications being released. So I just want to show you some applications just to get you motivated. Some of these applications you might have seen before, some of these might be new. This is an example of Microsoft Copilot, an excellent application for creating images. So here the prompt which I have given is a realistic giraffe playing games on a spaceship. This is something which Google will never be able to create because it's something which will first of all not exist, and the answer it gives in just 5 to 10 seconds, and it looks very realistic, which I can directly use in my work. The next example is that of creating PowerPoint presentation. So here is the presentation I created about the evolution of cricket in India, and within 1 minute this entire PPT was created. All of this is possible because of the advancements in the field of generative AI. Then this is text to video. What I have done here is that I simply gave an image of this volcano, and then generative AI actually converts that into a very realistic and gripping video. In case you are not aware of this application, it's called Runway ML. Then the next example is that of an acid rain. You can see on the left, it's a very static image, but the moment I give it to Runway ML, it identifies that there is probably some rain in the background, and you can see the spattering of rain. And imagine now this movie or this video being played with some background. It will look really cool. Then we can generate music from scratch. So let's say I've given song about rains, and I click on this song. A completely new song will be created, which was not existing before, based on the prompt which you have given. And then finally, generating 3D models. There are a number of applications in this domain also. So what is the main outcome of this initial section is you should understand what are the main applications of generative AI, and how much of an impact it's really having on all the spheres of our society. You pick any field, and there are applications of generative AI which you can imagine in that particular field. Now we'll go to the next section, and I will stop sharing my screen, and Sahil will start sharing his screen.
Okay, so let me start sharing my screen for the next section, which is evolution of generative AI. So I'm very excited for this session. So please be more proactive on the chat, ask your questions, ask your doubts as and when they arise, and try to get the maximum benefit from this lecture. We try to answer all the questions on the chat. So be active and try to get maximum information from this session. So my part, in the initial part, I will cover the evolution of generative AI. But before we go ahead, to make the session more interactive, we'll be asking a poll question. So if you go to the chat, let us just share the link where you can answer that poll question. Sahil, could you share that link maybe on the chat?
Yeah, I'm on it.
Sure, sure. So this is that. So this is that link. Is it pigeonhole.at?
Yes, yeah, that's the link.
Okay, so can you go to this link pigeonhole.at and type in the code Vizuara AI? Let me also try to do it. So if you go to pigeonhole.at, so if you go over here, guys, and let's enter. So you'll enter this room, then click on enter this poll. I don't know why this is showing for me, but hopefully for you, the first question is visible right now. Can any one of you confirm if the question is visible for you? I think the question should be something related to uh, yeah. So for some people it's showing it's visible, for some it's showing missed the question. Transformers related. Yeah, for me also it is showing oops. So whoever is seeing the question, can you just answer this question? Let me see if this is updating on our dashboard. So the event password is Vizuara AI. I can see that there are 62 participants here.
It might be showing miss because is there a timer?
Uh,
No, there is no timer.
Oh,
It's
okay.
so the code is this Vizuara AI.
Yeah, I'm also seeing, I also logged in as a participant and I'm also seeing missed the first question like this.
Oh. So if you are being asked to register, just create an account. That should be fine. Whoever is seeing this, at least you guys can answer this. Okay. Where can we? So let me see my admin panel actually. Yeah, for some reason it's showing missed the question. Okay, we can probably figure this out as we continue this webinar. In the meanwhile, Sahil, can you create this question on Zoom poll? Like Zoom itself has this poll / quizzes. Maybe while this is working, we can create it. I don't think anyone is able to answer this because I should have seen this score over here. So it's fine. We can proceed to the next part. So in my part, first I'll be covering the history of large language models, and you might be quite surprised at this because so how many of you are aware of this Eliza chatbot, which was released in I think around 1966? Just type yes or no in the chat. So many people are saying no, but some people are saying yes. So this was one of the first large language models, and let us actually interact with it right now, live. So I've chosen the language to be English right now.
Please tell me what's been bothering you.
So Eliza says, please tell me what's been bothering you. And then I say, I want to learn generative AI. Where should I start?
Why do you want to learn generative AI?
So then Eliza asks, why do you want to learn generative AI? Then I say, because I want a job.
What if you never got a job?
Then Eliza says, what if you never got a job? So as you can see from these answers, it's pretty bad, right? It's not sophisticated at all. In fact, some of the questions which it is asking to me and the way it is interacting with me, it is not helping me at all. And this was the state of LLMs in 1960s. So imagine if you were born in this time, we would not be conducting this webinar at all. So even before ChatGPT came into the picture, there are a number of things which people tried. So after ELIZA, this was the state of ELIZA in 1966. Then was the neural network boom. But the problem with neural networks is that you cannot capture memory or history with neural networks. So let me give you an example. Let's say in ChatGPT, you want to predict the next word, right? Given a paragraph. So for that, you need to have memory of what has come before. So to give an example, let's take this example, which is Harry Potter. Harry Potter went to the train station and he was looking for the platform. That's my first sentence. The second sentence is that platform was, and then I asked the LLM to complete this. Now, for the LLM to complete the second sentence, it should know the first sentence. So ideally, the answer should be the platform was missing. So the LLM should have some knowledge of what has happened in the past, right? What was the context of this? What was the previous? What was the previous at the start of the sentence? So what's the memory? But neural networks don't capture memory or history. So I can see now that the quiz poll is working. So maybe we can conduct that poll now. Can you all go to this link now? Pigeonhole.ai/Vizuara AI, pigeonhole.at/Vizuara.ai. Sreedath has shared. You can go to this link which I'm showing right now on the screen, and you can just click on enter this poll and then answer the first question. So let me check on this, what I'm seeing on this panel over here. So I can see that there are these many votes. But now I actually want to see the leaderboard. See, this is the leaderboard which we see right now. So, and you can see that it is updating live over here. So, which of the following models is not considered to be generative AI? GPT-4 is 4.5%, DAL-E is 2.1%, BERT is 42.6%, and Stable Diffusion is 51.1%. So, there is a pretty good competition between BERT and Stable Diffusion. We'll be coming to the answer in a bit when Sahil talks about GPT and BERT, but right now keep this as a curiosity in your mind. So voting has ended and answers have been revealed over here. I think you can also see over here. So the real answer was BERT actually. That is not an example of generative AI. You can see this tick mark over here. Many of you got it correct, but most of you got it wrong, and that's fine. We'll see the differences between generative AI and BERT models later. For now, let us continue with our history of generative AI. And up till now, we have seen that neural networks are not good because they don't capture memory, and we need memory when we are dealing with text. So then what happened between 1980 to 2017? Transformers or large language models didn't just come out of random. There has been a historical progression. So especially there are two main techniques which I want to briefly touch upon. First is recurrent neural networks, which came in 1980. And second is long short-term memory networks, which came in 1997. So these innovations happened in this period of 20 years, and then came transformers after 20 years. So if you see the gap, there is like a 20-year gap between successive innovations. But many people don't appreciate what happened before. They just start looking at transformers. We are going to come to transformers later in this lecture, of course. But for you to appreciate transformers, you first need to appreciate what is wrong or what went wrong with the initial techniques and how we can improve to reach transformers. Okay, so the first thing the first technique which came up was in 1980, recurrent neural networks. The main idea in RNN is that it's like a traditional neural network, but it introduced a hidden state like this, or a hidden layer. See, this hidden layer was the main innovation in recurrent neural networks. And what this hidden layer did was that it added some sort of memory to the neural network. And that's why RNNs became so popular. And we could do some things with RNNs such as generate sequences of text, music, etc. So let's say, for example, if you want to predict the stock price for this company whose stock is varying like this blue line over here, you want the data from all the preceding days, right? You don't just need the data from day 9. You would ideally need the data from day 1, day 2, day 3, dot, 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 up till the day 9. So we need our neural network to be flexible in terms of how much sequential data we are using to make a prediction. We need our neural network to capture memory so that it takes all the previous days into account. Traditional neural networks don't do this. So recurrent neural networks actually exactly do this. They take into account the previous input values also. So let me show you the schematic of a recurrent neural network. The main part which I want you to remember is this feedback loop over here. In traditional neural networks, all the arrows flow in a linear manner, right? You go through one neuron, then the second layer, and then the output. In recurrent neural networks, you have this feedback loop. What this feedback loop essentially does is introduces some kind of memory into the system. Along with the present values, it allows the recurrent neural networks to have past values also while making the prediction. And this feedback loop here makes all the difference. So the feedback loop makes it possible to use sequential input values, which is basically to encode memory, and it helps us to make predictions about the future. The problem with feedback loop is that if you want to, let's say, capture memory which is long back in the past, you need to chain multiple feedback loops together. So for example, if you want to capture memory 5 days back, you want to chain 5 feedback loops together. And what this leads to is that it leads to this kind of a vanishing gradient problem, right? Where the different gradients multiply with each other and all of them are less than 1 or greater than 1. So either the gradient vanishes or the gradient explodes. That was the biggest problem with recurrent neural networks. But the takeaway from here is that recurrent neural networks introduced this feedback loop to capture memory, but they had this vanishing gradient problem. Then what did people do next? Before we come to LSTM, there is the second poll, which we want you to answer. So can you go to the same link now, which is this link? Let us share it again on the chat. Where is it? Let me find it. Yeah. So I'm sharing this link on the chat right now. It is the same link. Can you guys go to this link? I will also go to this link simultaneously right now. And let's see. So you can again enter the poll and you can answer the second question now. Who is credited with the initial development of recurrent neural networks? Try to answer this. Let's see how it changes. So here, this is the live answers from 116 participants. I encourage everyone to apply answer. I can see around 200 participants in this call, but only 113 have responded. Please be more active and try to participate here. Okay, so 115 participants, 83, 85 votes so far, and again it's split. So I can see that the questions are good because people are confused. It's kind of split between option 1, option 2. Many of you might be perhaps Googling or asking ChatGPT, but it's fine. You can answer quickly. We can also see on the projector panel. Okay. Yes, we can.
Next, I think the result will be displayed.
Okay. So now I'm clicking on reveal. Okay. So let's see over here. The correct answer was David Rumelhart, and 40% of you guys got it correct. So good job. Now let us move next. So recurrent neural networks are good, but they have this problem of vanishing gradient, right? So what people did next was they moved to something called long short-term memory. What this did was that along with having a short memory, which is what recurrent neural networks had, like along with having knowledge of yesterday, long short-term memory also incorporated knowledge from some time long back. So basically, it had short-term memory and it had long-term memory also. That's why it's called long short-term memory. So it has two paths. One path is for long-term memories, and one path is for short-term memories. So it turns out that this solves the vanishing gradient problem. I won't go into this LSTM architecture, but basically there are two lines which go through the architecture. The green line, which is the long memory, long-term memory, and the pink line, if you see over here, that's the short-term memory. And basically, these long-term memories and short-term memories work together to make the predictions of the future state. So this is better than RNN, and it does a better job of incorporating memory, but still it is nowhere compared to where transformers are today and what ChatGPT does. So the real innovation came in the 2017 paper on transformers, which we are going to look at henceforth. Okay, now let us come to the third poll. So can you guys again go to this link? Actually, we can see a leaderboard over here. I did not know this leaderboard existed. So see, we can see the rankings. So try to be better at this next question to improve your ranking over here. I guess this is the link, and let me track. So if you click on enter the poll, this is the third question, right? What is the primary advantage of using LSTM networks over traditional RNNs? LSTM automatically sort input data. LSTM are capable of learning long-term dependencies. LSTMs eliminate the need for activation function. LSTMs guarantee constant time processing regardless of sequence. Just try to answer as best as you can. Let's see. So we have 70 votes, and almost everyone has answered that LSTMs are capable of learning long-term dependencies in the sequential data. Awesome. Please answer quickly, because in 2 to 3 seconds I'll be ending this poll and revealing the answer. Okay, so 123 participants, 107 votes. Great. So let's reveal the answer now. Most of you are correct in this question, which means that you have understood this concept. Actually, now where was that? Here we can see the leaderboard. As you can see, Yashwant is currently the top scorer. Actually, there are many top scorers who have got all three correct. Precisely 18 people in this call have gotten all three answers correct so far. So we'll be conducting 3 more such questions. So please be more attentive so that your rank can increase. Now we are going to come to transformers. But before we come to transformers, you should understand one thing, that transformers are awesome. They are very cool, right? But the input to the transformers is words. So let's say this is a French sentence, which is an input to the transformer. What the transformer can do as one of its capabilities is translate it into English. But first we need to understand, how does transformer recognize these words? Because humans can look at it as words and sentences, but not computers, right? So we need to convert these words into some sort of vector representation, which then is feeded or as an input to the transformer. So before understanding the transformer architecture itself, we need to understand how words themselves are converted into vectors. And this process of converting words to vectors is called as word embedding. So we are now coming to the next section, which is called word embedding. So why do we need to represent words numerically? Because computers need numerical representation of words. They cannot just look at sentences like we do. So, okay, you might say, what if I assign random numbers to each word? So let's say cat, I assign 34, book, I assign 2.9, tablet minus 20. The problem with this is that cat and kitten are actually close to each other, right? But if you assign random numbers, it does not capture the semantic relationship between words. So assigning random numbers is definitely not a good approach for word embedding. So then you might think, what about one hot encoding, right? So let's say I create this one hot encoding representation for as many words which I have, and then I just put one based on that word, and remaining will be zero. So dog will maybe look something like this. Puppy might look something like this. Again, this is a big problem because there is no semantic relationship here. Dog and puppy should ideally be close to each other, right? One hot encoding also does not capture this semantic relationship. Then we have this very cool idea. So I have 4 words here: dog, cat, apple, and banana. What if for each of these words I have some features such as has a tail, is it eatable, has 4 legs, makes sound, and is a pet? And then I give values based on these features. So if you look at dog and a cat, have a tail has a higher value, right? Has 4 legs has a higher value. Makes sound has a higher value. Is a pet has a higher value. But if you look at apple and banana, has a tail has almost zero value. Has 4 legs has zero value. And is a pet also has low values. So if these are the values of these words, dog and cat will now lie close to one another, because if you see this, they kind of look similar, right? These vector representations. So this gives you an understanding that if these words are represented as vectors in high dimensional spaces, so here these words are represented as vectors in a 5-dimensional space, and that can help us capture the semantic relationship between words. Dog and cat here are closer to each other. Apple and banana are closer to each other. So vectors can capture semantic meaning, and that's why every word will be represented as vectors. So here there is only 5 dimension, right? But in real life, the words are represented as huge number of dimensional vectors. And how this vector embedding is generated is through training a neural network itself. So now I'm just going to show a quick Google Colab notebook to show you vector embedding, or word embedding rather, and then we can move to transformers. So let me share my screen to show you a Google Colab. I think you still see this. Okay. a minute.
Do you want the link, Raj?
Yeah, I got it.
Okay.
Okay, so this is the Google Colab notebook for vector embedding. It's a pretty nice notebook, and I'll actually make this link public and share it with all of you in the chat right now so that you can also take a look along with me. So I've put it in the chat right now. Please click on this link and access it. Okay, so here what we are doing is that we are already using a pre-trained vector embedding model, which is trained on Google News, and it's trained on billions of data. And here you can see this 300 represents the dimension. If you remember the Canva presentation, we had 5 dimensions, right? But here we have 300 dimensions. And this is already a pre-trained neural network. We are not going to train this. But I just want to give you some sense of how words can be represented as numbers. So if you, let's say, use this vector embedding and you want to see the vector representation of computer, you can see that here is the vector representation. There are 300 dimensions. So this is a 300 dimensional vector for a computer. And now you can actually do some very cool things. Like for example, vectors can be added and subtracted, right? So what if you add the vector of king to the vector of woman and then subtract the vector of man? So ideally what you're doing is you're adding a masculine aspect plus a feminine aspect minus a masculine aspect. So what should remain is some feminine aspect, right? If you are capturing the semantic relationship. So let's run this right now. And you will see that, look at the result. The result is queen, which means that it is kind of retaining the semantic aspect, and it makes sense, right? King plus woman minus man has to be equal to queen if you are capturing the semantic relationship. You can even check the semantic relationship magnitude between words. So woman, man, king, queen, uncle, aunt, they are related to each other, right? So you can see their similarity scores are much higher. But if you plot the similarity score for paper and water, let's say, it's very low. So that's why this is again a proof that the vectors have some meaning associated with them. They are not random. We can even plot the difference between the vectors. So for example, man and woman, the difference is 1.73. Nephew and niece, it's 1.96 because they are kind of related to each other. But if you plot the difference between semiconductor and earthworm, you can see that it's very, very high. So there are some questions in the chat about which similarity score is this showing? Is it the difference or something? Yeah, it's actually, if you look at how it's calculated, so here it's the vector difference between, it's the magnitude of the vector difference between those two words. So imagine two vectors sticking out in space. The difference between the vectors, it's this magnitude of the difference between the vectors. And I'm calculating a normalized score. So I'm dividing by the magnitude. So that's why you can normalize it, but I'm currently not normalizing it to be between 0 and 1. You can do that also. So this is the basic intuition of word embedding. As you can see, I did not go into too many mathematical details here because that is not the scope of today's workshop. So today we want you to get an intuition of what word embedding means, so that when we come to the transformers part, you will not be lost when Sahil talks about word embeddings and how they are fed as input to the transformers. For now, just remember that words are converted into vectors like this. So every input to the computer or to the AI model is not a word, but it's actually a vector. If you remember this, that would be a good takeaway from this particular part. Okay, so I'll stop sharing screen here, and then Sahil will take care of the next part, which is the introduction to transformers.
Yes, thank you, Raj. Let me just press it. I hope everyone can see the screen right now.
Yeah.
Let's minimize this. All right. For those of you who don't know me, my name is Sahil Pocker. I work as a machine learning engineer at Vizuara AI Labs. Right. So far we've talked about all of these sequence to sequence models, right? Like RNNs, LSTMs, and all of that, even Vertex, all of that. And these are before 2016, let's say. And what happened in 2016, 2017, around that time, is the advent of the transformer architecture, the attention is all you need paper. So this was revolutionary in several ways. And by the results itself, we can see that just after that, even GPT, T5, BERT, Palm, GPT-4, and all of the AI revolution, the generative AI revolution, was kind of, in a way, ignited by the advent of transformers, I could say. You could argue that there are other things like some may be thinking about generative adversarial networks also. But yeah, this is what created a lot of difference. If you look at Google Translate, for example, I'm not talking about generation at this point, but just about transformers. So when you look at Google Translate, if you looked at it before 2016, let's say 2014 or so, it wasn't that great for people who've been using it since then. And after a while, let's say from 2017 onwards, Google Translate started becoming really, really good. And that is because of this architecture. So one of the main advantages is that before we talked about sequence to sequence, right? If you want to translate something, we fed whatever sequence we had step by step. With transformers, the advantage is that you don't need to explicitly pass the first token first and then you get it translated when you pass the second token. You don't do that. You don't do it in a sequence manner. Rather, the main advantage is that it is highly parallelizable. It is parallelizable in several places, but mainly the input is not given in a sequence. Rather, all of the input tokens are given together. So if you take a very simple model, maybe it's a very small input context length. You can only maybe give a sentence or something, but later on, like models like GPT-4 and very advanced models has a very huge context length. That's like 128,000 length and so on. The main thing is that it is not in any kind of order. It is completely randomized. The advantage of this is that we are not limited by waiting for each token to process. Rather, all of these go through parallelly. Like if that is, I'll give you an example so that that becomes easier to grasp. Like if you have just one stove burner, and if you're cooking something, then you'll need to probably cook that, take it off, put the next thing, take it off. And then that would take a lot of time. But at the same time, if you had like 4 stove burners, you could do a lot of things in parallel, right? And it is kind of an analogy so that you can pass all of the input tokens in parallel. And like I said, all of these are interdependent, all of these input tokens. And by tokens, if I take this sentence as an example, transformer, encoder, and decoder, maybe transformer is one token, encoder is another token. It is split like that, right? But we need to know that the first word is in the first place. And that is why we add something called postural encoding over here. We don't need to go into depth about postural encoding, but understand that we just add a small value to the input embedding. Like earlier, we saw that each token was represented by uh, a series of numbers, right? And right now, what we add a small value to that to signify that the first word is in the first place. And this would be understood by the transformer model itself. I'll get into how they do that next. Okay. Yeah. So before going into the entire model, this might be quite intimidating at first to look at, I'm sure, but there are a lot of components here. But let me start by going through one of these components one by one. And one of the main things in transformer-based models is the attention, right? So we'll get into attention first. So that is here.
Sahil,
So,
Sahil, there is one feedback from the chat. Can you just be a bit louder?
oh, yeah, sure.
Yeah.
Yeah. Right. I'll just... Okay, so now that we've seen the entire figure, but I know that it is a bit complicated. Now what we'll do is we'll look at one component at a time. So we'll look at the multi-head attention. That might be quite intimidating. What does attention mean? What is multi-head? All of that, we'll get into that. So the main idea here is that in attention, if you have a sentence, let's say the animal didn't cross the street because it was too tired, something like that. When you have it later over here, we don't know what it exactly means, or the model wouldn't know. Even if you use LSTMs and all, it is very difficult for it to have that context. And this is just a small sentence. Imagine if it was a huge paragraph, or if it was a whole page. Then if you say it at the end of it, it is very difficult to say that, okay, it means this particular thing which was before, that is the animal. It's very difficult to do that. So the main ideas of attention is that even though we have all of the words together, each of these words can pay attention to certain words, right? And let's say this is an example which I already gave you, that if it is it, and then these two, the animal will be having a higher attention value there. That means that it is paying more attention to that. This is done mathematically in a more complicated manner, which I won't be getting into depth in this webinar. But understand this much, that the input is fed into the first attention layer, and then we do it such that we do a series of multiplications such that, okay, let me go to the next slide, and I think you can see it better here. In a normal convolution or a fully connected layer, that is like in a normal dense neural network, what happens is that you have all these weights, right? You have all these weights in the first layer, you have in the second layer. And even in convolution, you have the first layer, and then it just convolves. Or maybe if you want to detect an edge, then it just detects the edge. It just goes to that next point. But what you change is the values of these neural network layers directly. But with attention, an additional thing is that you can see all of these arrows, right? That means that you can change how each of these each of these values pay attention to the next, whatever the next token is. So there is some kind of connection in between them. Let me just go to, all right. So if I revisit this, and let me give you a simple example of translation, how it would flow through. I haven't still gotten to the feed forward or the multi-headed attention completely, but I'll give you an idea. So I told you there's the encoder and then there's the decoder, right? So if you have an English sentence and you want to convert into French or so, you input it, and then you of course have the embedding, and then you add the positional value, just to say that which word comes first, which word comes second, and all of that. And then you have these encoder layers. That means n into encoder layers. You can have one, you can have six, you can have a lot of encoder layers. And then what the encoder layer does is it creates a representation. That means that it creates a middle representation. So if you actually try to calculate, if you actually try to translate what this English word, and if you know some other language like French, how to translate that, you first have a representation in your head, right? And then after that, you translate it into the French part. So something similar happens over here. You have a middle representation, and it is of course a matrix and all of those values, just the mathematical values, but still what the encoder in effect does intuitively is that it creates a middle representation. And what the decoder's job now is that it has this access to this context or this understanding of the first sentence we fed it. Now the decoder starts to generate words one by one. And if you look at this figure, you can see that there are a lot of similarities between this encoder block and this decoder block. And there are some slight differences between them that we'll get into what this mass multi-head attention means, but multi-head attention, and that is quite similar in both of these cases. I will also talk about how it actually predicts a word in the decoder stack. So one thing to notice is that even though this is made for translation, and one important thing to note is that the transformer architecture originally, when it came out, it was intended to solve the problem of machine translation generally. It was to translate from one language to another. That was the main target. But at the same time, they realized that you have this context, right? And then you're modeling the language somehow. You're having some kind of an understanding in the language. So from there, naturally, we realize that if we have the kind of understanding, maybe we can generate text with that understanding. And a lot of possibilities opened up. But it all started with machine translation. But another thing is that even though we have this encoder decoder stack here, because this we use for translation, and some of the transformer based models use this kind of a model architecture. But at the same time, if you look at something like GPT, the GPT doesn't have encoders at all. So in this webinar, we'll look a bit more into depth about how GPT-2 generates a word. Even though I won't go into so much depth about this base model, I'll go into GPT-2. And also there are other models like BERT, which just have encoders, and there are different combinations. There are some decoders and there are some encoders, and all of those combinations. But if you look at GPT-2, you have a decoder-only architecture. And in GPT-2, you have 12 stacks of these. That means you have 12 decoder stacks. So you just feed in an input, and then you have all of these 12 decoder stacks, and then you get the output. And I think it's a good time for a poll right now. Let me just go here. Think of, can somebody click next on the admin panel? I think.
Yeah. I can see the new question now.
Click next.
Yeah. You can. Yeah, people have started voting.
Yep. I think you can. All right. I think we are at 81 votes.
Sahil, do you want the admin link?
No, I have the admin link.
Okay.
I'm just waiting for the votes to match the participants, then I'll reveal the answer.
Yeah.
All right, I think I can reveal the answer now. Yep. Okay. Google Brain was the answer. Was
Sahil, we are still seeing your canvas screen, I guess.
yeah. Let me just resume.
Yeah.
Right. Not okay. Okay. Yeah. Can you see it now? Is it still not visible?
Right now, your screen is not coming. Just I think the screen sharing has stopped. Yeah. Now we can see.
All right. Okay. There is one more question I need to ask you. Okay. Think. Okay, this is. This. Let's give you some more time and then I'll go to next. I'll get to the answers of this, of course. I'm trying to know like what you know about this, like what kind of an idea you have so far. And this means to allow the model to focus on different parts, different aspects of the input sentence, by the way. I think it's not complete. Okay. I think I'll reveal this answer. Okay. Yeah, it is. I'll explain how that works in a bit. Just before that, okay. All right. So share this again. Okay. Yep. So the thing with single head attention is, and before that, let me also show you this. So like I said, we have several layers, and each of these layers, if you look at a single word, let's say, and each of these are different attention heads. Like I told you, one attention head, what it could do is it could probably point that the animal, or like if you go to it is probably the animal or something like that. But if you look at some other attention head, it might be focusing on something else. It might be trying to understand something different, or like extracting some different kind of features from the input sentence, right? And if you look at this, yeah, if you look at this, you have this masked multi-head attention, and then you have the final outputs over here. So our final goal in the decoder-only architecture over here is to find some word. What is the highest probability that the next word is this? So if we have a vocabulary list, we are trying to predict what word comes next. So that is our goal, right? So what all of these stacks do is that in the first stack, let's say you realize or you recognize some of these features, that this word is particularly paying this much attention to these other words, and this other attention head focuses on different features. Maybe some of the attention heads try to understand which part of these words are nouns, which of these are verbs. And some of them might be doing something like, okay, if you have it over here, what is it pointing to? What is the connection between it? And this is not programmed before. Rather, it is learned by the model one by one. As in, we have such a structure that if you let the gradients flow through it, the model will learn all of these features. We won't be able to exactly pinpoint what each of these attention head does, but each of these attention heads are designed such that they learn particular features of the model. All right.
Why is the screen frozen? There is the present, that thing is appearing, present full screen.
Okay, let me try again.
Yeah.
All right. So another thing with the decoder block as compared to the encoder block is that there is something called the masked attention. As you can see over here, we have the masked multi-head attention. And this is because in the other case of self-attention, it could be that we can understand all of these features between all of these words. Let's say if we use it over here, we can easily see that it can connect to other words. But from generating a new word, you don't want them to peek forward, right? So if you're generating a word later on, you don't want to peek to the words which are coming later. So what we do is we mask it. We mask all of the later on words. So if you're at ease, you won't be able to access all of these later words. All of them are grayed out. That is the difference between normal multi-head attention and masked multi-head attention. And this only in the decoder block. And the only thing we do is we put a curtain over the future occurring words so that we only have access to the words which we have, the words which we have generated currently. Okay, now I'll illustrate that in a bit. So before that, one additional thing is the feed forward layer. So maybe if I tell this, you'll get a more connection about how the whole thing works in a better manner. So I told you they have masked multi-hit self-attention, and you have maybe 12 stacks of the whole thing. And you have this feed forward and the layer normalizations, right? So after the multi-head attention, that we gave some kind of an output that, okay, these features are extracted and this is what this word relates to the other words in this manner. That is what the information, what we extracted so far. And what a feed-forward neural network does is, a feed-forward neural network is just a normal neural network, like two linear layers, like a general neural network. It doesn't have any recurrent connection. It has nothing like that. It is just a normal neural network. And it has a non-linearity introduced in between them, and that is a rectified linear unit. And what it does is it creates some space for the model to understand even more complex topics. So if you have just one block over here, let's say, it might realize something. Like if you say a word like it, and then you have the animal, it can connect those two words, like simple one-level connections it can make. But at the same time, if you have several layers and if you have these feed-forward networks in between, it is able to stack all of these features up. And then it can recognize even more complicated features. And that is why even in GPT-2, we have 12 of these stacks. It still does a great job of generating content. Let me just give you a demo of GPT-2 right now. This is okay. Let's try a word prediction, and this is a simple sentence.
Sahil, we are seeing your Canva screen. Are we supposed to see?
No, the code screen. Let me just share.
Yeah.
All right. Okay, now I think I can see. All right.
Yeah.
Okay. Yeah. So this is directly from Hugging Face that I'm just implementing GPT-2 directly. And we'll try to find what word is predicted after this particular sentence. All right. Let me just run this. Yeah. And then you can see that over here we have the outputs and we predict the next word after this. And these are the output probabilities, as you can see here. And you can see that the right answer is, of course, not here. And this is because when you train GPT-2, probably there wasn't enough information, or maybe the GPT-2 model is not sophisticated enough to understand this question and generate the next word. Maybe I'll not ask it such a difficult question. Maybe I'll ask it to predict what the next word here means. If I say natural language, let's see what it does. You can see that, all right, it's generating something. I can try it again. Let's see what happens. All right. Right. The next word is generated with and, in, and all of these with this probabilities. And this is because GPT-2 is not such a strong model. It just does something simple. Let me see what they'll generate if I do this. All right. Okay, GPT-2, I think it's not that great of a model to generate really good results with, and especially with a small context. But let me show you like how exactly GPT-2 generates that final output. So we have the decoder stack output, right? As in we have all of these decoder stacks. We have, let's say, 12 stacks for GPT-2. And we have, in each of these stacks, we have the masked multi-head attention. Let me just go back here. We have the masked multi-head attention and you have the feed forward. And you have 12 stacks of these. And in the end, yeah, you have this final linear layer, which gives you these logits output. And then you run it to a softmax so that you get the output probabilities. So you just distribute it. So you get some values. Let's say if you want a certain word, if you have a natural language and the next word you want to predict is processing. So ideally that will have a high value. And when you distribute it using softmax, it will be weighted such that that word will have the highest probability and the other ones will have lesser probability. And then the model will output that word. So that is how this model is trained. But at the same time, let me also talk about how this actually is a neural network. You might be seeing all of these blocks here and there, but you clearly don't see a flow happening through all of that. Even through multi-head attention, you can't see a direct flow happening, right? And this is also a huge problem. And you, as Raj already discussed in LSTMs, we have this vanishing gradient problem. We do a lot of calculations and we miss the actual information and then the gradient disappears. So ideally in a neural network, you have forward propagation and then you see, okay, there is some error and then you do back propagation and you do corrections, right? And you slightly change the gradients. But over here, we go through all of this processing and we might lose the original gradient flow, what is happening. So we have what you call these residual connections as well. So if you just look at a neural network like that, we have the input over here, and then it goes around the masked multi-head attention. and then it goes around the feed-forward neural network as well. And then you can see these new layer normalizations. What they do is that we take the output from the multi-head attention as well as whatever input we had originally, and you add both of them together. It's kind of like a mix. You take some from the multi-head attention and some from the original input, so that you don't essentially lose all of the original input. And then you do that again over here. And this is one of the key things in transformers that makes it work really well, which is all of these residual connections. You can see it in a simple encoder block as well. You have these residual connections, and you have this feed forward. And it passes through all of that, and finally you have the decoder stack output. And even in the decoder stack output, you can see that after the final layer normalization, you have some part of the input still here. And you get the final output from there. Let me give you more illustrative example of how this is. So you of course start with a start token. This is something which I missed, that we have a certain sentence. Like if you're generating some word, we have some other special tokens. There is a padding token, there is a start token, there's the end token, so that we can signify a sentence ends, a sentence starts, etc. So when we are generating a sequence, we give the start token at first. So we feed the start token to the model and it goes through. So this shows 2 decoder stacks over here, but maybe we have a lot of stacks. GPT-3, for example, we have, let me go here. I think if you can vote on the final question, we can see. Can you see the question?
Yeah.
All right. I'll just let you vote and guess how many. All right. Just wanted to finish off this question also. I can see the final leaderboard. I'll continue. Okay, so the correct answer was 96 attention heads. Oh, here we have very small number of attentions. Even in the original paper, we have a very small number. We have like 8 attention heads, 16 attention heads. We have small number, but right now we have huge models such that the number of attention heads itself is huge, and the number of layer stacks is also very high. Right here, we have 2 decoder stacks, and in the right. Okay. Yeah. In the next iteration, what happens is you get the output, as in it goes through and it produces the log probabilities through the softmax, and you get robot as the output. Now what happens is it is fed back into the decoder layer. As you can see in this over here, whatever is outputted over here, it goes back. Right? And now we have access to that word also. And now our job is that to find what word comes after robot. And it keeps on going until the model generates the end of the sentence token. And then you finish the sentence. All right. Okay. If you have any more doubts about this, I think we'll take it in the question section. I'll hand over to Sreedath for.
Yeah, thanks a lot, Sahil. So from the comments, we understood that the encoder-decoder part will need little bit more explanation, but that's very natural because we only plan to cover in so much detail in like a half an hour session. So I think it'll be a good time to introduce a course that we have recently launched on our website. So this is something where we teach transformers from its theoretical standpoint, its intuition, and also building the transformer, basically as some LLMs from scratch. So this we have, we'll share the link. We have spent maybe like last 6 to 7 months making this course, and in this process we also have learned a lot. So I remember like Sahil, Raj, Rajat and I, we discussing in meetings, there is a concept called position embedding, and the way in which position embedding is implemented for in GPT and in several other LLMs is in a very interesting way. And we had just meetings to just discuss for 2 hours how does this position embedding work. Oh, critical error. Is anyone able to access? Oh, everyone is having error. I'm able to access for some reason. Okay, we'll see. I think it will fix itself. I don't think it's a problem. Anyways, yeah, guys, don't panic. We'll share the link to this website once again so that you will not see the. But you can see my screen, right? There is I can access it fine. So we'll share it. So what I will be doing is what Sahil has showed is the basic structure of a transformer, and what I will show you is how to run your own GPT kind of from scratch. So maybe some of you have heard of this person, Andrej Karpathy. He was part of OpenAI, then he went out, then he came back. I don't know if he again went out. I think he's not part of it anymore. But Andrej Karpathy had released last year a video on his YouTube channel. It has 4.5 million views, although it's 2 hours long and it's incredibly dense. This is an amazing video. I don't know if many of you have gone through this fully, but basically what he is doing is he is building a GPT completely from scratch, and he has named this GPT as Nano GPT. Nano because it's very small in terms of the number of parameters. And what we will be doing is we will be forking his repo. So this is his GitHub repository. I'll just share the link. I don't want you to follow me while doing the code or anything. Just you can sit back, relax and listen. And after the lecture, you can try this yourself. But basically, this is the link that I put in the chat to this GitHub repository, and just look at the number of stars. It has 35.3k stars. It's a huge number of stars. Many people have forked it to work on it themselves. And I will just show you briefly how does this look like, how does this Nano GPT look like visually. So let's first look at GPT-3, right? Currently we have GPT-4o. What you see here is, if you zoom in, each of these cells are kind of denoting parameters, and there are in GPT there are probably 70 billion, 50 billion, large number, I think 175 billion or something like that parameters. Recently in the Llama I think there was 405 billion parameters or something. Nano GPT is, as the name suggests, it's much smaller. You can see that I'm zooming in so much. If I click on GPT-3 here, you have to zoom out so much, and Nano is like a dot here. So Nano GPT is very, very small. I will not walk you through this entire 3D diagram. This is also a beautiful website. I highly recommend you to go through this. All you need to do is go here and click. You see these play buttons. Just click the play button, and it will automatically show the animation of what will happen to tokens, and it will take you maybe 5 or 6 or 10 iterations through this to even get some idea what's happening here. But basically it's very simple. You have let's say you have a sentence. Each word can be considered as a token, although strictly that is not correct. In this case, you have some alphabets as the token, and then these set of alphabets will form like your entire context or entire input, right? So your input to the GPT is C, B, A, B, B, C, and C is represented. So the numerical representation is 0, 1, 2, 0 for A, 1 for B, 2 for C, right? It's oversimplified. And then what happens is something called as token embedding is created, and token embedding is something that Raj already showed. So token embedding is basically same as vector embedding. And so these tokens, each of these tokens are converted into, I think this is what, how many dimensions? I think this is 48 or something. I forgot. I think this is like a 48. So each token, like each A, B, C is converted into a vector of length 48. And then you can do a bunch of operations. But I'll just show one thing here, which is the multi-head attention. So many of you were asking in the chat, what exactly is attention? So attention is nothing but, if you just look at this matrix. Just look at this matrix, attention matrix. Let me go back to. Do you see this matrix? This is basically a square matrix, and this is an example of what is attention matrix. And what is that? It's basically if a sentence has 5 words, let's say a cat sat on a mat, something like that. So cat and mat has a certain relation, a degree of relationship. Cat and sat has a degree of relationship. So these are different words, and you can define a degree of relationship between these words, and you can represent this degree of relationship as a set of numbers in the form of a 6 by 6 or 7 by 7 matrix. So the reason why in GPT and in many other transformer architectures we call something as multi-head attention is because if I zoom out, do you see multiple attention matrices here? There is one here, another one here, another one here. So in this example, if I remember correctly, they have 3 attention heads. So here the multi-attention head is 3 attention head. In GPT, in the example that Sahil asked, there are 96 attention heads. So you will see 96 such repeating attention matrices back to back. Okay, so this is Nano GPT. I'll not go into details of this because this is not my intention. Let's come back to the Nano GPT. Here what we will be doing is I will show you how we can train a GPT, a small GPT completely from scratch, and we'll be training it on a particular data set. So on Kaggle, there is this data set called Spotify million song data set. So basically it has description of, so it has song name, and there is like a lyrics of the song. So lyrics of the song is basically how you describe the song, right? So lyrics define what is the content of the song. So what we will be doing is we will be training our Nano GPT on this data set. It has large number of rows, and basically I think it has million songs. And what we will be doing is we'll be training a very small small sized GPT. So the Nano GPT itself can be in different sizes, different versions. Since I am running on my own computer, which is not a very high-end configuration computer, I'll be using a low-end version of the GPT. And I will show you how you can create some gibberish. Gibberish meaning I'll give some token, some Q, and using that Q, it will generate a song. And the song will be based on whatever it has been trained on. So there is this huge data set, okay? So we can fork this repository by clicking fork. And if you click fork, basically you take a copy of this repository on which you can work on yourself, and it will be part of your own repository. So here I can choose Sreedath as the owner, but I have already forked this. That's why you see here fork already exists. But don't worry about these terminologies. I am fully aware that not all of you are probably aware of these terminologies. Simply understand that I'm just copying the repository for all practical purposes. Then what we do is now Andrei Karpathy's Nano GPT repo is now here in my GitHub. So now what I'll do is like I'll open this the code using this software called GitHub Desktop. So GitHub Desktop I use because I'm too lazy and I don't like to code in terminal. So I just operate GitHub using this GitHub Desktop software. I highly, if you use GitHub,
Sreedath, you're muted.
oh, is it? Am I audible now?
Yeah.
Did I just become muted?
Yeah, just right now, 2-3
Okay,
seconds.
thanks. Yeah, thanks. So what I was saying was I'm fully aware that there are a lot of files that you see here, but don't pay attention to any of that. I'll just show you 1 or 2 things that you should look at. So firstly, we have dataset here, and the dataset that I'll be using is the Spotify dataset. So I have created a folder here. In that folder, I have the CSV file, which is the Spotify million songs dataset. I downloaded this from Kaggle, okay? Now what we will do here is all the parameters of Nano GPT is already defined here, but I will just show you in 3 minutes of training that we can do on my computer, what kind of really bad output you can produce. And although the output is bad, you will still be amazed to see that, okay, if on my normal configuration Mac, if this can be the sort of output that I can produce in 3 minutes of training, imagine what I can do with maybe $10 million in money and a huge set of GPUs, what I can accomplish. And that's exactly what you're seeing in ChatGPT. So here what I will do is I will first prepare my data set from the CSV file. So from the CSV file, we extract it and we put it in a way in which we can use it. Don't worry if you don't, don't worry for the fact that you are not understanding this code. I have no intention to make you understand this code, but I just want to show you the output. So I'll prepare the data set and I will start the training in a moment. So now then I'll go to train Spotify and run this. Don't worry if you don't understand anything. So here one thing I want you to note is, can you see this line? I don't know how big my screen font size is. There is a line called unique characters. So what these unique characters are, you can see most of the English alphabets in capital here, most of the English alphabets in small letter, and a bunch of special characters, numbers. These are all the different characters, unique characters appearing in our training data set. And what is the training data set? Training data set is nothing but the Spotify data set. So these are the characters that are appearing in the lyrics or in the entire data set that in the CSV file. Sometimes you will notice that, if we were training on just a few different songs, sometimes these letters which are less used, X or Z, these alphabets may not be appearing in some songs. So if for whatever reason in our training data set, these alphabets were not there, you will not see this as part of the unique characters. Anyways, so we have done the training, we have done the data set preparation. Now, what we will do is I have already, put the training code ready here so that I don't have to type it down while I am presenting. So I'll share all of these things with you. So don't worry about any of this. And we anyway have a full-blown video on this, but I just want to show you how quick this is. So here we have defined bunch of training parameters so that it is a little bit, convenient for my CPU. I don't have a GPU access. So right now we'll be training for 2000 iterations, and you will see that once the training starts, okay, can you see this iterations and the loss? So initially in the first iteration, you have a loss of 4.3, and we are going to run 2000 iterations, and it's pretty fast. And you can see that the loss is gradually decreasing. Basically what's happening here is the Nano GPT, the previous 3D model which I showed you, it is getting trained on the CSV file, which includes the name of some songs and the corresponding lyrics. So that million song data set. So this Nano GPT is now being trained on the data of those million songs. And you will see, I will stop the running of the iterations even before 2000. I don't think running for 2000 iterations is necessary. But actually, let me stop right here and show you how bad this is. So I just interrupted the execution at 500 iterations. Okay. Now, at this 500 iteration, let's say I ask my Nano GPT to create a song, and I can give a cue. Maybe the starting could be some word like sunset. So you see this, whatever this gibberish that this model is creating is supposed to be some song that has got something to do with sunset. You see how bad this is? It barely looks like English. You can see English alphabets, but most of them are meaningless, right? There is no meaning here. Like what do these things mean? So because I trained the Nano GPT only for 500 iterations, it could not learn words and semantic meaning between words that well. So that is why the output looks so bad. Now let me go back to training so that I can show you with more number of iterations, basically more training, how this thing can improve. So I'll take a screenshot of this because you may forget how bad this was. So I'll show you maybe if you forget how bad the original output was. Okay, now let us run this once more. So this time, let's wait patiently. It won't take more than, I think, 2 to 3 minutes. So let's wait until at least 1500, 1800 iterations are done. For some reason, it's a little bit slow right now. But this is a beautiful demonstration of how GPT works in principle. And if you really want to learn the operations of transformer completely from scratch, so we originally what we did was we were trying to follow Andre Karpathy's 2-hour video for building our own transformer, but the problem was it was still too dense. I don't think 2 hours was enough to kind of a 2-hour video was not sufficient to teach a beginner all the different complexities in a transformer. So what we decided was we thought we will create an even more simpler version of the transformer, kind of almost from scratch. So the course that I shared earlier, let me try sharing the link to the course once again, and please tell me if you are still facing the error in the website. If not, it will be great. If there is error, no problem, we'll fix it. Can you guys check this link? Is there still the error occurring? I've shared this course link. Guys, let me know if there is error or if there is no error. Okay, error is not there, working. Okay, awesome. So yeah, it just fixed itself. I did not do anything. Anyways, so just check out this course, guys. So this course is structured in such a way that the entire transformer architecture we have divided into meaningful chunks. So originally we did not intend to make this full-blown course, but as we started learning transformer more and more, each time you read the attention is all you need paper, you will learn something new. The prerequisite for this course is maybe, I would say, okay, this is a very subjective question. So, but Vedant, if you ask the prerequisite, I would say the only prerequisite is a state of mind in which you are willing to put some number of hours. So this is really not a crash course. It takes a lot of time. There are several assignments that we have embedded, and also this is like a living course. So what we mean by that is we have several interesting modules that we have planned in large language models, which are like hands-on, so that you can learn. So we plan to keep on adding those material to the course. So I think that's the only prerequisite. I don't think you need to know too much about LLMs or even the attention is all you need paper. And yeah, so it's a paid course. It's not a free course. Please check the website. Then let me come back to the transformer. I mean the Nano GPT. Can you see my Visual Studio Code right now?
Yeah.
Okay, so the iterations are almost finishing. We were planning 2000 iterations initially. Yeah, so iterations have finished. Now let us check how the output would look like for the same. We gave the sunset as the initial cue, right? So let's give the same thing and let's see how the output looks like. So now, do you see the kind of output you are getting? It is definitely English. It's still not good. You see sunset. It has already made some spelling mistake, but definitely you can read it now. It is garbage for sure, but lesser of a garbage compared to what it was before. And we trained it only for 2 to 3 minutes. So and this has no meaning. Like it was to Moore, I'll solve. I don't even know what these things mean, but definitely many words are English. It's much more readable. I don't think there is any meaning, but this is what Nano GPT is. Now, if we can accomplish this using a normal computer with 3 minutes of training, imagine what you can do with tens of millions of dollars and 400 billion parameters. That is what you are seeing right now in Llama 3 or in GPT. So I will do one thing. I'll stop sharing my screen so that Sahil can show you a few more interesting things. Yeah, Sahil, you can take over.
Yeah, thank you, Sreedath. Let me just share my screen. Right. Yeah. So there's a lot of things you can do with generative AI. Let me just skip. to this slide. Yeah, there's a lot of examples. There's text generation, which we were doing with GPT or even Nano GPT right now, or GPT-3, and there is text classification. We can use BERT for that. And there is a BART, which is like a variation of BERT. And all of these models are like based on the same transformer model. Like, of course, you know that. And there is also something interesting over here in the multimodal space, as in where you involve audio, video, etc. also with the same transformer model. This is like the vision transformers. I cannot get into details of how vision transformers work, but understand that like instead of convolutional neural networks where you like directly pass the pixels, like you try to pay attention to certain pixels, certain regions, and that seems kind of intuitive. Even if you suddenly look outside and in the wild, if you see something, you automatically pay attention to certain sport more than all the other sports together. So that's something which vision transformers did. You can definitely read about it. I'll also give it some detail about that in the course as well, about vision transformers. And there is also speech recognition, wave to vec. It also helps. It's a lot of these uses of applications of transformers. And let me give you, I've prepared like 2 demos over here, and one is text summarization. Like, and if anybody can give me a text, I can try their text as well. I'll like run this for now. This is just a simple text, right? And this is using BART. It's a variation of BART on Facebook. It is just running. Meanwhile, let me check if somebody's giving me. Right. Nothing. Give it a second to run. Okay. You can see that we had this huge paragraph, but then now it's been like summarized pretty well by this model. This is a very small model over here, like BART, especially compared to, this is not a small model. And there's something interesting also, like with the nomenclature that you call large language models as large, but it's just that it is in such a scale. The even BART won't be such a small model. It is also pretty big, but it's just that current large language models like GPT-4 has a lot of parameters that it belittles all of these models in size and parameters. Another thing I want to show is something with vision transformers. And all of this is using Hugging Face itself that I'm running, that I'm not coding all of this from scratch. And in the course, I also have a place where I'm coding all of these parts like self-attention, where I'm explaining what self-attention is and also implementing it and each of the parts in self-attention too, so that you have a more in-depth understanding. Over here, we're just directly using, and even in real world, sometimes we can directly use all of these models, but it is of utmost importance that you understand what the model does in the inside, so that you can do more fine-tuning, or you can change things and you can adjust it to specific applications. If you're directly doing this, you're just summarizing a sentence, you will only need to directly load it. But if you want to improve on it, then you'll need to understand how that works. And okay, let me just run this. And I think I'll need to find an image. Let's say, let me just find a picture. Let me try to get the URL of that. Okay. And let me try this over here now. Okay. This is running. This model over here, what it does is it just directly labels it, just gives a label for whatever image you give. And this is not using convolutional neural networks like you would use generally. This is rather using a vision transformer. It is a transformer which helps, what do you say, pay attention to certain regions in an image. The only reason why vision transformers are not used so much in the real life is because of the computational cost. The convolutional neural networks are very efficient sometimes in just this particular image generation task. And in applications, you might need that efficiency. But at the same time, vision transformers are also it has a huge potential to, and it works in a similar manner. And it is quite amusing to see that it works across several modalities. Even when you're generating music and even generating other things, the transformer model architecture is so powerful that you can use that in all of these modalities together. Let me just waiting for this to run. Yes, does VIT have more computational time? Yes, as compared to CNNs, it might, because CNNs are very direct. This is a slightly more complicated model, and even ChatGPT, etc. Even for text generation, it is a bit resource intensive to run and to train to. So yeah, vision transformers is slightly more computation time, but there are a lot of research happening in vision transformers and a lot of optimizations happening such that it is reduced a lot. Let me wait for that. I don't know why this is. We have time to run. Okay. Meanwhile, I'll just share this. I think the final standings of the poll also had come. And I think one person had got all of the questions correct. A lot of people got all 5 correct, but I think a shout out to Ramesh for scoring all 6 somehow. Congratulations for that. Let me go back here now. And congrats to all of these people who came in the top 6. I think for some reason this is taking some time to. I think I should try a smaller image, maybe. Try that. Okay, that URL didn't work. Right, just give it a moment. I think I'll post this for now, and then I'll get back to it when it comes. Let's see. All right, it actually did come. I think it was because of the size of the pixel. Yeah, so you get the caption directly from the vision transformers. You're not using a convolutional neural network here. It's completely that. I think the caption is generated. Yeah, I just wanted to show you like some of the ways which you can use transformers directly. And this is all using Hugging Face. And to use this, you just need your access token, which you can just get if you go to Hugging Face, go to settings and get to access tokens. You can generate one and you can use it. Collab, you can play around with it. And good luck with that. Yep. I'll just stop sharing now. And
Awesome. So there are a lot of questions in the chat. However, we are already running a few minutes extra time. I'll just do one thing. In the permissions, I'll allow all of you guys to have video access to enable your video. Yeah, so I have enabled video switch on. So guys, we can take like a snapshot if you guys can switch on your video. So our plan is we'll be definitely be conducting more hands-on workshops and webinars on transformers. It is actually a difficult topic, so you should not expect to understand it in a very meaningful way in like 2-3 hours. If you can do that, it'll be magic, but we don't know the recipe to that. So obviously it's going to take some time. but we will be conducting bi-weekly, most likely bi-weekly or once in a month frequency webinars, and we'll be covering different topics, and all the assignments and hands-on material will be posting in the course. So whoever is part of the course will be getting access to that. But thanks for attending, everyone. We can take a picture. Last time we did something like this. Feel free to make whatever pose you want to make so that it will appear good on camera.
Who is taking the screenshot?
I am taking.
Okay.
Awesome. So thanks for attending. All of you will have work tomorrow morning, right? So thanks for attending so late night for this event. And if something is not very clear, and if you still have doubts, you can email us. We'll share our email in the description. If you have missed any link, or if you have missed any GitHub repository or course link or GitHub or the collab link, don't worry, we'll be sharing everything plus the recording link on your email. So so we'll be sharing everything with you. But
Thanks,
hope you enjoyed it, and thank you so much. Feel free to give any last minute remarks.
See you in the next webinar. I can see some participants from the SciML bootcamp. Like I can see Vedant. Good to see you, Vedant. I can see few others from the SciML.
I can see Sharv somewhere. I saw Sharv is there.
Good to see you, Sharv. Okay, guys, great to connect. We'll see you in the next webinar.
You guys have a good night. Bye.
Bye, guys.